This lesson will introduce you to dimensional analysis. Sometimes you'll hear it referred to as the factor label method. Largely what this is just a method for you to convert units of measure from one unit to another. If I were to ask you the height of this box, you could look at the picture and you could kind of look at your frame of reference. You could say, well, it's sitting on the ground and it extends up to about where the doorknob is on this door behind it. And so you might say, well, that box is 3 feet tall. Okay, if I were to ask you how many inches tall is that box, you'd think for a moment and then you would say, well, 3 feet, that box is 36 inches tall. Okay, what you did there automatically was dimensional analysis. You probably weren't thinking of it in that fashion. You were probably saying, well, in every foot, there are 12 inches, 12 times 3, 36. The box is 36 inches tall. In actuality, what you were doing was that calculation, and it looks something like this. Okay, so you knew the box was 3 feet tall, and then you knew that there was a relationship between inches and feet. And you know that in every 1 foot, there are 12 inches. So feet cancel feet. 3 times 12 divided by 1, 36 inches. That is dimensional analysis. Because 1 foot and 12 inches are the exact same thing, you can make a fraction out of them, and the fraction will be equal to 1. So if I have like 1 foot over 12 inches, or I could say it the other way, I could say 12 inches is 1 foot. Because these things are equal, they are essentially equal to 1. Anytime you have a fraction that the numerator and the denominator are identical, that fraction is equal to 1. You're probably familiar with this from your math classes, but anytime you multiply a measurement by 1, it's not going to change the value of that number. So here in this example, I multiply 5 by 17/17. Guess what? It's 5. When you're multiplying fractions, recall you multiply the numerator and divide by the denominator. One thing that you need to be really aware of is that it does matter how you set up the conversion factor, which value you put in the numerator, which value you put in the denominator. It really will change your answer and the meaning of it. For example, let's say I want to convert 100 yards into feet. You guys are familiar with 100 yards. That's the length of a football field. So let's start out with what I know, 100 yards. And let's say I want to put 1 yard is 3 feet. Okay, so whenever you're multiplying numbers times fractions, you multiply the numerator, divide by the denominator. So 100 times 1 is 100, divided by 3, 33.3, repeating. And you may say the units would be feet, but they're actually not going to be feet in this instance because a yard times a yard would be a square yard, and then per foot. Those units are even nonsensical, so that's not, there's another indication that you haven't done it correctly, is that you come up with weird units, square yards per foot. Nobody knows what that is. Okay, let's look at the next one. We could have done it, we could have said 100 yards. Well, every 1 yard is 3 feet. Notice when you have units in the numerator and the denominator, because even though this number 100, you're like, well, it's not a fraction. It really is. It's 100 over 1. So notice that doesn't change the value of 100 yards. So the yard unit is in the numerator of a fraction. Okay, yards will cancel yards. You're left with units of feet. That's awesome. So I take 100 times 3 and divide it by 1. So you get 300 feet. Now, if you stop and think about this logically, which one makes more sense? Think of a football field. Is a football field more apt to be 33 feet long or 300 feet long? Well, the obvious choice is 300. And so hopefully you can see how this illustrates. Even though those fractions are equal to 1, it does matter which one is the numerator, which one is the denominator. One thing you need to be aware of is that units used for conversion factors, they are generally considered to be defined quantities, and they do not count towards significant figures. I'll give you a quick little refresher on significant figures. Probably the easiest way, that Atlantic-Pacific rule. Probably the easiest way to recall this, if you think of a map of the United States, and you notice over here on the west coast you have the Pacific Ocean, over on the east coast you have the Atlantic Ocean. So as long as you know some basic geography, the United States, here we are, Omaha, you remember the Pacific is on the left, Atlantic on the right. If the decimal point is present, start at the Pacific. Present, Pacific, both start with P. You're going to begin to count on the left hand, the Pacific side of the number, and you move from left to right, and you will start counting at the first non-zero, and then everything beyond it. And so here are a few examples with the number 306.4000. Starting from the left, because there is a decimal point, you will notice that there are 1, 2, 3, 4, 5, 6, 7 significant figures. The number 1200 written with a decimal, there are 4 significant figures because you start at the Pacific side, 1, 2, 3, 4. And let's see this next one, 10th, 100,000, 10,000, 100,000. So we have 400,000ths of something. Notice there is a decimal point, so we start at the Pacific side. The first non-zero is 4, there's nothing behind it. That is only one sig fig. The others are simply placeholders. If you need more significant figures, you put a 0 at the end. So notice the 0 at the end does count. So none of these count. The 4 and the 0 do count. This one has 2. If the decimal point is absent, you start at the Atlantic side, so the right side. So you'll go from right to left. And so in an example, here's 1200 written without a decimal. No decimal, these don't count. The 2 and the 1. 1200 written this way has 2 sig figs. 1207, okay, the 7 counts. 1, 2, 3, 4. 4 significant figures in that example. I'll just refresh your memories dealing with the rules for multiplication and division according to significant figures, largely because this is going to be the math operation that we use about 98% of the time. Just recall that you must round your answer so that it will have the same number of significant digits as the measurement having the fewest. And so really, you know, if you think about it, your rounded answer can only be as accurate as your least accurate measure. And that makes sense. The nice part about dimensional analysis is that you can use it to convert between dissimilar units of measure. So for example, you know, the English imperial system, the one that we're all familiar with, to the metric system or the SI system, the one that the vast majority of the rest of the world uses. This map demonstrates the countries that still use the English standard system or the imperial system. So we have the United States, this tiny coastal African country is Liberia. This is Burma. So really only 3 countries in the world still use the imperial system. Here's a hint that the imperial system isn't super awesome. See this? It's England. It's kind of named, the English standard system is named after England. They don't use it. That should give you some hints. And you may wonder to yourself, you know, why do we cling to this outdated system of measures if everyone else in the world uses the metric system? And the only reason why we continue to use the imperial system, simply tradition. One of the major shortcomings of the English standard system is its weird conversion factors. And it's got a lot of vocabulary, you know, it's things that you don't really pay attention because we've grown upon, you know, with this our entire lives. You know, everyone in the United States knows that 12 inches is a foot. 3 feet is a yard. You may not know the yards to a mile, but the 5,280 you're probably familiar with feet in a mile. What's kind of interesting is that where some of these units came from. For example, the measure foot was really supposed to be the length of a man's foot. Looks like I should have got a penny before I snapped this photo. An inch was the length of 3 barley corns, whatever a barley corn is. A yard was supposedly the distance from the king's nose out to the tips of his outstretched arm. The unit mile was supposed to be 1,000 paces. And so you can see some definite problems with these units. They weren't necessarily standardized. And not only that, it's difficult to convert from one to another because you have to remember specific numbers, and the numbers aren't always the easiest to remember. The nice thing about the metric system, one thing you'll also sometimes hear me refer to it is the SI system. It stands for System International, the international system. It's convenient because it uses a series of base units and then prefixes to make them larger or smaller. And they also happen to be based upon units of 10, so it's really just a matter of moving the decimal place to convert to make something bigger or smaller. You will notice that the unit for length is the meter. Meter is generally abbreviated with a lowercase m. That's a really sloppy lowercase m, but it's a lowercase m nonetheless. Let's see if I can clean that up. There we go. The volume, liter, is a common one. Liter is a capital L. Mass is a gram, lowercase g. The amount of substance is a mole. You're going to become very familiar with this term, this unit. There is an abbreviation for mole. It's not much of an abbreviation, but it is MOL. I guess you get to save the pen stroke for the E, but that is a mole. When I'm talking about an amount of substance, it's just like any other thing, like a dozen is 12, or a pair is 2. A mole is simply a number. And then temperature, many of you might have thought that units for temperature in the metric system would be Celsius. Actually, we use Kelvin. That's a temperature scale you may not be familiar with. The thing that's different between Kelvin and Celsius, Kelvin has no negative degrees. There is a lower limit of temperature. It's 0 Kelvin, sometimes also referred to as absolute zero. We'll learn about that when we get into the gas law units. Kelvin is just abbreviated with a capital K. Notice there is no degree symbol, it's just Kelvin. This chart shows a number of prefixes used with the SI system. The ones that we'll use quite often, well, here's the base unit, just the base 1. In chemistry we'll use kilo quite a bit. Kilo means 1,000. Notice it's abbreviated with a lowercase k. Other common ones, deci means 1/10, lowercase d. We use centi, which is 1/100th, lowercase c, and milli, which is 1,000th, lowercase m. Those are the ones that are fairly common. There are times when you will see like micro, which is a millionth. You recall we already used nano when we talked about nanometers and we were speaking of wavelengths of light, so they're billionths of a meter. There are some other things you will see on here. You're familiar with terms like gigabytes, billions of bytes, or even now some hard drives on some devices have like terabytes, which is 1 trillion. And so those are some common ones, but I mean, if you get these kind of central ones down, that's good enough. One nice thing about the metric system is that it's very simple to convert units from one unit to another. This is a common diagram you will see. Notice it's got, you start here with they call it the bench, but you can call it the base unit. As you move down, so let's say you wanted to go from meters to centimeters. So just for an example, let's say I have a stick that is 1 meter in length and I want to convert that to centimeters. Okay, so I start here at the base unit, the meter. I go down the steps, 2 steps. That tells me that I must move the decimal to the right 2 places. And so there's an understood 1 there. So if I move it to the right 2 places, 1 meter is 100 centimeters. And that makes sense. If I wanted to do a conversion going the other way, let's say, I measured like something, and let's say it's 67 centimeters, and for whatever reason I want to know how many kilometers that is. So you start here at centi and go into kilometers. I go up 1, 2, 3, 4, 5 steps, and so basically you do the same thing. I would take the decimal, and this time you got to move it to the left, and I'm going to start, it's understood to be after the 7, so I would go 1, 2, 3, 4, 5. So it'd be a decimal here. So that would be, let's see, tens, hundreds, thousands, 10,000, 67 hundred thousandths would be the units in kilometers. Okay, I'm going to give you guys a chance to practice. I want you to convert your height from inches into centimeters, only given the following conversion, that 1 inch is 2.54 centimeters. So go ahead and pause the video at this time and see if you can do this conversion and set it up correctly and get an answer that makes logical sense. Yeah, the first thing you really have to do is you have to know your height in inches. So let's just say, for sake of argument, I can't do everyone's individual one, let's just say you are 5 feet 6 inches tall. So the first thing is you have to convert that into inches. Well, 5 feet, we're going to do some dimensional analysis early. I know that in every 1 foot, there are 12 inches. Feet cancel feet, 5 times 12. That tells me that 5 feet is 60 inches. And to this, we're going to add the 6 that we left off from the 5, 6. So if you were 5.5 feet tall, you were 66 inches tall. Now I know a conversion from inches to centimeters, so I'm going to go ahead and start with what I know. So I know my height is 66 inches tall. And let's see, I know that for every 1 inch, there are 2.54 centimeters. And so what I'm going to do is I'm going to punch this into my calculator. 66 times 2.54. Your calculator is going to spit out, let's see, 167.64 centimeters. Because inches cancel inches. The only unit you're left with was centimeters. And that looks good. Now, according to significant digits, our answer can have no more significant digits than our measurement having our least. These are not measurements. These are defined values. This is a measurement, 66 inches. This means that this is your height accurate to the inch. So you knew, within 1 inch of how tall you are, but 2 units. So we have 2 sig figs in our answer. So we must round 167 to 170 unit centimeters. So this would be the correct answer with significant figures. And as you did that last problem, your answer should have been in the range somewhere between 150 centimeters up to somewhere near 200 centimeters. This would give you a range of roughly 5 feet to about 6, 7. And that's probably, you're somewhere in between there. I didn't see, that's generally about the size of, I would say most adult people would fall in that range. The nice thing about using dimensional analysis is that you can do more than one step. You don't have to do it in just one conversion. Here's an example. Let's say I want to convert 27 kilometers into miles. But let's say I don't know a conversion factor from kilometers to miles or vice versa. Let's say the only one I can recall is 1 inch is 2.54 centimeters. And honestly, to be truthful with you, I don't remember kilometer to mile conversion, but I do remember for some reason 1 inch is 2.54 centimeters. So let me show you how you would do this type of problem. As always, you start out with what you know, 27 kilometers. Okay? Well, I can get it, I need to get eventually to centimeters, right? Because I'm in the metric system. How am I going to convert kilometers down to centimeters? Well, I'm going to get it into the next smallest unit. So I know that in 1 kilometer, there are 1,000 meters. That prefix kilo means 1,000. So 1 kilometer is 1,000 meters. Kilometers cancel. And now I can convert meters down to centimeters because I know in 1 meter, if I look at a meter stick, there are 100 centimeters. Centi means 1/100th. Meters cancel. I now have centimeters. Now that I know centimeters, I can go from centimeters over to inches. So we're halfway home. So on the bottom, I'm going to put 2.54 centimeters is 1 inch. Those things are equal. Centimeters cancel. My answer is now in inches, but I don't want inches, I want miles. I don't know how many inches there are in a mile, but I do know how many feet there are. So I know that there are 12 inches in 1 foot. Inches cancel. And then I know there are 5,280, that's an 8, feet in 1 mile. Feet cancel feet. And so now I'm ready to solve. I grab my calculator. I'm going to multiply 27 times 1,000 times 100. And then I'm going to divide by 2.54, divide by 12, divide by 5,280. And so if you do that in your calculator is going to spit out a number that looks like this, 16.777. The units would be miles. Observing significant figures. Notice we have 2 sig figs and 27, so we have to round our answer to 2 sig figs. The answer would be 17 miles. And you're not simply limited to only doing 1 conversion at a time. You can convert more than 1 unit. An example of this, let's say you're in a car, you're traveling down the highway at 55 miles per hour, and you want to know how fast the car is traveling in meters per second. You would do this in the exact same method. What I would suggest is you're doing problems like this, I would write 55 miles per hour in this fashion. 55 miles in 1 hour. Because that's really what it means. 55 miles in 1 hour. So if you look at this, I need to convert, and it doesn't matter which one you do first. Let's convert miles into meters. All right? And once again, let's just say that I do know a conversion, and let's say that somewhere I learned that 1 mile is 1.609 kilometers. Maybe I looked it up on Google or something. Okay, so I can go from kilometers then to meters fairly easily. Since I know this equality, I know I'm going to put the 1 mile on bottom. 1.609 kilometers goes in the numerator. Miles cancel. I now have kilometers, but I didn't want kilometers, I wanted meters. And so I know that in every 1 kilometer there are 1,000 meters. Kilo means 1,000, so 1 kilometer is 1,000 meters. So now, if I were to stop and solve at this point, the units would be meters per hour, but I didn't want meters per hour, I wanted meters per second. So therefore I'm going to have to convert hours to seconds, but that's no problem. I know that in 1 hour there are 60 minutes. So hours will cancel hours, and then I know that 1 minute is 60 seconds. Notice that I'm always putting the unit I'm trying to cancel on opposite sides, so like hours was in the denominator, so I had to put the hours in the numerator. Same way with the minutes. And so now, looking at the problem, the units I have left are meters per second, which is awesome. That's what I was looking for. So I'm ready to start calculating. I grab my calculator. I take 55 times 1.609 times 1,000 divided by 60 divided by 60 again. And what it's going to give me, it's going to give me a number that looks like 24.5872. So I look at my initial measure, it only had 2 sig figs, and let's round this to 2. The answer, 25 meters per second.